Ladies and gentlemen, welcome back to lesson 17 in group theory. In this lesson, we're going to be answering the question, if I had two subgroups, H and K, what happens if I combine them together and I get HK? Well, this is what we call the composite set. So we'll be defining it, and then we're going to calculate its cardinality using Lagrange's theorem. Afterwards, we're going to be seeing exactly when this composite set becomes a group. We call it a subgroup of G. And the last thing is that we're going to see that the index of a subgroup is multiplicative. That means it will be easier to calculate the index of subgroups inside subgroups. Let's get started. The definition is fairly straightforward. Let G be a group and H and K two subgroups in G. The composite set, HK, is defined to be H times K for all elements H in H and all elements K in K, which is a subset, of course, of G. Let us now move on to proposition 1, where we calculate its cardinality. Let G be a group, H and K subgroups of G. It's important that they are finite subgroups. Then we can calculate the cardinality of HK to be the cardinality of H times the cardinality of K divided by the cardinality of the intersection of H and K. Let's get to the proof. To prove this proposition, we will start by rearranging the elements in HK. We will say that HK is equal to the union of small h times big K as H ranges through H. So essentially saying this is equal to H1 times K1, H1 times K2, H1 times K3, all the way until we finish all the elements of K, and then we start with H2, and then we repeat the same process. H2 times K3 all the way, and then H3, H4, until we finish all the elements of H and of K together. So this is nothing but a rearrangement of the elements of HK. Writing it in this way gives us the liberty to write it in terms of cosets of K. So we have that two cosets H1K and H2K are equal if and only if H1 inverse H2 is an element in K, as you already know from the cosets lesson, and this is if and only if H1 inverse H2 is in the intersection of H and K. This is true because we already know that H1 inverse H2 is an element in H, since H is a subgroup of G. So we have that these two cosets are equal if and only if this element is in the intersection. And this, now we use the definition of the coset, but the coset this time is H intersecting K with H1 and H2 to say this is if and only if H1 H intersecting K is equal to H2 H intersecting K. So these two are now the equal cosets based on this verification here. So we have that two cosets of K are equal if and only if two cosets of H intersecting K are equal. So following this if and only if statement, if we take the set of the cosets HK as H ranges through H, and we take the set of cosets of H intersecting K as H goes through H, and we take the number of elements in this set, and we take the number of elements in that set, we find that these numbers are equal because of this if and only if statement. But on the right-hand side of the equation, we find that this is the cardinality of H intersecting K. This is the set of cosets of H intersecting K, which by Lagrange's theorem equals the quotient of the order of H and the order of H intersecting K. And on the left-hand side, we find that this is the cardinality of the set HK when we take it the quotient by K. Because these are the elements of HK, and we're taking the cosets of K, so this is exactly what it would look like. And again, by Lagrange is equal to the order of HK divided by the order of K. The only thing left for us is to rearrange the terms now. Since we have this equality here and here, all what we gotta do is multiply by the order of K in both sides, and we're done, proving the first result. The second question that we need to address is, when is the composite set a group? And the answer lies in proposition 2. Let G be a group. Let H and K be subgroups in G. Then the composite set HK is a subgroup of G if and only if HK is equal to KH. Note here that HK is equal to KH does not mean necessarily that the elements of H are commutative with the elements in K. That means we could have that HK is equal to some element K1 and some element H1, not necessarily saying that K is equal to K1 or that H is equal to H1. Let us now start by assuming that HK is a subgroup in G. It is a subgroup, that means it is closed with respect to the operation of G and with respect to inverses. So since K is a subgroup of HK, because it's a subgroup of G, so therefore it is a subgroup of HK, and similarly H is a subgroup of HK, we have that KH is a subset of HK. And the reason is that because HK is assumed to be a subgroup and it's closed with respect to operation and inverses, and both K and H are inside HK, then the product KH, the composite, has to be inside HK as well. For a more formal approach, I would invite you to try it out as an exercise. Now, since HK is a subgroup in G, then if we take an element HK in HK, then the inverse of that element also lies in HK. If it is inside HK, then that means this element here is equal to H1 times K1 for some H1 in H and K1 in K. And if we work on the left-hand side, we find that K inverse, H inverse, is equal to H1, K1. And this, of course, is in KH, because this element here is in K, and this element is in H, because K and H, again, are subgroups closed under inverses. So we have just proven that HK is contained inside KH. So now we have proved the double inclusion, and we can say that HK is equal to KH, proving the forward direction of the proof. Now suppose that HK is equal to KH, we would like to prove that HK is a subgroup of G. So to prove it's a subgroup, we have the two-rule thing where we prove it's non-empty and that it's closed with respect to operation and inverses in one go. So HK is non-empty since 1 is in HK. The identity lies in HK because the identity lies in H, the identity lies in K as their subgroups, so it lies in their composite set, HK. The second thing is that if we have H1, K1, and H2, K2 in HK, we would like to prove that H1, K1 times the inverse of H2, K2 is also in HK. So this is equal to H1 K1, K2 inverse, H2. Note that H1 is in H and K1, K2 inverse, H2 inverse is all in KH because this is in K as K is a subgroup and this is in H as H is a subgroup. So all of this is in KH. But we know, we've supposed that KH is equal to HK. So this element is in HK, this element is in H, so combining them together, H1, K1, K2 inverse, H2 inverse. Can you see this? This is in H and this is in HK. Therefore, all of this is in HK. But this is exactly this element here, which is in HK. So now we have proven that HK is a subgroup of G, completing the proof of the backwards direction and the proof of proposition 2. Let us now look at an example using this proposition. So if G is the dihedral group D to N, H is the subgroup generated by R, and K is the subgroup generated by S, then HK, the composite set, is going to be RS, and that is defined to be R to the K, S to the L for integers K and L. But this is exactly equal to the entire group D to N. So if it's equal to the entire group, then HK is a group. In particular, HK is a subgroup of itself, G. If it's a subgroup, then by proposition 2 above, we have that HK is equal to KH. Note that this does not mean that the elements of H commute with those of K, because as we all know, SR is not equal to RS, it is equal to R inverse S. Let us now have a look at a nice example using the symmetric group and a dihedral group. We will be using both propositions in this example. Let G be the symmetric group of 4 elements, S4. Let H be the dihedral group of a square, rotations and reflections of a square, D8. And let K be the cyclic subgroup of S4, which is generated by the 3-cycle 1, 2, 3. So here immediately we see that K is a cyclic group of 3 elements: the identity, the 3-cycle 1, 2, 3, and the inverse of that 3-cycle 3, 2, 1. So the order of K is equal to 3. Now, we know that technically H cannot be a subgroup of G because H has symmetries while G has permutations. So it is not a subset of G. However, H is isomorphic to H prime, which is in fact a subgroup of S4. What is this isomorphism given by? This isomorphism is given by taking each symmetry in D8 and associating it to a permutation of the vertices on which the symmetry sends these vertices to. So for example, if we had the square with vertices 1, 2, 3, 4, and the symmetry will exchange the places of 1 and 2, then the associated permutation is going to be the 2-cycle 1, 2. And this is defined for all of the symmetries of D8. So technically, we can kind of say that H is a subgroup of S4 because it has the same structure. So technically, even though we cannot say outright that it is a subgroup of S4, it has the same structure as a subgroup of S4. So we're going to be abusing notation here and replace H prime by H, okay? But I'd like you to always keep that in mind, that we're not dealing with H here, we're dealing with H prime, which is a subgroup filled with permutations, not symmetries. Anyways, knowing this, we know that the subgroup is order 8 because D8 has order 8 and we have an isomorphism. So in an isomorphism, the two groups must have equal order, 8, 8. Great. So we have that the order of H is equal to 8 and the order of K is equal to 3. Now what I claim here is that the intersection of H and K is the trivial subgroup. The intersection of H and K is the trivial subgroup containing only the identity permutation. I will be proving this claim a bit later, but for now I will treat it as fact. And if this claim is true, then the order of H intersecting K is equal to 1. And using proposition 1 and this claim here, we can calculate the order of the composite set HK to be equal to the order of H times the order of K divided by the order of H intersecting K, and that is equal to 8 times 3 divided by 1, which is 24. But 24 is equal to 4 factorial, and that is equal exactly to the order of the symmetric group of 4 elements S4, as we've seen in the lesson for symmetric groups. So HK is a subset of S4, but they have the same number of elements, therefore concluding that HK must be equal to S4. In other words, the composite set H and K together form the entire symmetric group S4. And because it is equal to S4, which is a group of course, then HK is a subgroup of S4, and by proposition 2, we have that HK is equal to KH. What a satisfying result that is. Just by calculating the order of HK, we get this nice equality here. Now, we need to prove that the intersection of H and K is the trivial subgroup. To prove this claim, let us have a look again at the orders of H and K. Let G be an element in the intersection of H and K. We want to prove that G is necessarily the identity element. So since G is in the intersection, it is in both H and in K at the same time, we have, by Lagrange's theorem, or rather a corollary to Lagrange's theorem, but I digress, we have that the order of G, the order of an element, always divides the order of the group it is in. So it always divides the order of H, and the order of G divides the order of K. The order of H is equal to 8, the order of K is equal to 3, but because 8 and 3 are co-prime, they share no positive factors except 1. So the order of G is forced to be equal to 1. And therefore, G is forced to be the identity because the identity is the only element whose order is equal to 1. That means that the set H intersecting K is just the subgroup containing the identity. Completing the proof of this claim here and the fact that HK is equal to KH. The last topic of discussion is proposition 3 saying that the index of a subgroup is multiplicative. That means, formally speaking, that if G is a group and we have a subgroup H inside a subgroup K of G, then the index of H in G is equal to the index of K in G times the index of H in K. The proof of this proposition is a pretty straightforward combinatorial argument. We will write G to be the disjoint union of the cosets of K, where I ranges through big I, and K is equal to the disjoint union of cosets of H, as J ranges through big J. Now, for each I, we have GI K, this coset, is equal to GI times the disjoint union KJH, J and J. But this is exactly equal to the set containing the disjoint union GI KJ H for J and J. So this is for each I. So what if we combine all of the GKs? So combining all of the cosets of K, we get that the group G is equal to the disjoint union of I going through I, J going through J, GI, KJ, H. So basically, since we said for every I in I, we have a set of cosets, GI, KJ, H, then if we combine it for the number of I's, we get this total thing, which equals to G. And so, if we take the number of these cosets of H, this will be equal to the sum of I ranges through I, and for each I, we're going to range through J of how many cosets there are. So we'll be counting cosets of H. And this is equal to the sum as I ranges through I of the cardinality of J, because this one is added for each J in J, so this is equal to just the cardinality of J, and this is equal to the cardinality of J times I in I of 1. Since this is independent for each I, we can just take it out, and we're left with the counter for how many elements there are in big I. This is equal to the cardinality of J times the cardinality of I. But the J here is defined to be the number of cosets of H in K, and the I is defined to be the number of cosets of K in G, thus giving us the result that we wanted. And that is it. If you enjoyed the lesson, drop a like, subscribe, and share with anyone who would be interested in this nice topic. I'll see you all the next time, and bye.